So, chemists, how are you? Doing well? Well, I'm doing very well. And I'm very excited to give you guys the opportunity this Friday to do a midterm. In which you can once again show us the teaching how well you understand the theory. Okay, so the midterm is going to be conducted in exactly the same fashion as the previous midterm. So that basically means you can use an index card, okay, as before. And you have allocated seating as before. We'll try to start on time as before. And you have 15 minutes as before. And as before, we'll have a practice midterm as well, which will be posted tomorrow afternoon. Okay, so you can have a look at that, get an idea, once again, of what kind of questions to expect. On Wednesday, the entire lecture on Wednesday will be devoted to reviewing material for the midterm. I posted already a little blurb online on the class webpage that says that the midterm will cover all the material that was covered in lectures 11 to 18. Okay, so lecture 11 was the lecture that followed right after the first midterm, and lecture 18 was the lecture that talked about acid-base reactions. Okay, and everything else in between will be part of the midterm. And that implies that redox reactions will not be part of the midterm, but it will be part, of course, of the final. Okay? So Wednesday we'll spend all the time needed to talk about the midterm and to go through issues. You may ask me questions. I'll have, yes? Yes, the question is if the final is cumulative, and that's correct. The final covers all the material from the beginning to the very end of this course. Okay, so everything. Yes? The question is whether I am going to have a review session. I am still debating whether I should and what time it would be. So I'll think about it and I'll try to organize it. Okay, so there are review sessions. Here is one. Okay, so the peer tutors from the chemistry department are having a session on Wednesday from 7 to 9 p.m. So you can attend that. And probably I'll try to organize something on Thursday, but I can't guarantee because of other commitments. I'll really try to make the time available. I also have office hours on Wednesday morning. If you want to come in or discuss things by appointment if possible. Okay, so today's lecture is a little odd because it does not comprise material that we cover in the midterm. Nonetheless, this will be in the final, so your attention is appreciated. And it touches on a very important aspect, which is balancing redox reactions. Okay, so we'll go through this and take note because this will come back at you. Okay, so first of all, let me show you this just to get your attention. And beautiful fireworks, the beautiful colors and the hard explosions that you hear are due to redox reactions. This is a beautiful example of it. One of the reactions that takes place in some of these beautiful colors is the following. This is sodium nitrate, and it decomposes spontaneously. Okay, not quite spontaneously, you have to set it on fire to ignite it. But then what it does is the nitrogen gets reduced and the oxygen gets oxidized. Very interesting. So this compound generates oxygen gas. Okay, this reaction is rather colorful. It's a little orange color, I believe, if I'm not mistaken. And this oxygen then subsequently is reacting with sulfur that's also present in the material and reacts really vigorously to form this compound, in which sulfur is this actually like the oxidizing agent, okay, which is being reduced and sulfur is being oxidized. So this is a beautiful example of two consecutive redox reactions. This one adds explosive character to the reaction, and this guy adds color to the reaction. Another example is actually in nature, where plants and organisms like yourself need to generate energy out of different sources, and we have very dedicated machinery to do that. And in plants, that happens in these membranes. In our bodies, it happens in mitochondria. And the machinery responsible for that is a set of proteins. We don't go into the details, but one very important step in generating energetic molecules is a redox reaction. That is basically this one here. There's more, but this is a very important one. NADH, which is the name of this molecule, okay? You don't have to know exactly what it means. Maybe you do, actually. If you have biology classes, you probably know what it means. This molecule is oxidized. You may have seen this reaction before, okay? So this molecule is oxidized, it generates 2 electrons, and also generates a proton. This proton is going to be very important for the proton motor force, and this electron is subsequently catalyzing several other reactions. Okay? So key step here in the energy production in organisms is a redox reaction. This way of writing things is kind of interesting. So this is an oxidation step in an oxidation reduction reaction. The reduction step is not shown here. Okay? So this equation here, this kind of like symbolic equation, is what we call a half reaction. And writing half reactions is one of the most intuitive methods of understanding redox reactions. So let's focus on that. Let's focus on half reaction and see what they can tell us. So we have already seen the following reaction, and this is the combustion of methane. Here's methane, here's oxygen, it forms CO2 and H2O. We've already concluded that this reaction, combustion reactions in general, are redox reactions. Okay? In redox reactions, there's a reduction step and an oxidizing step. Okay? So we could split this reaction in 2 parts. One part where a substance is being oxidized, which means it loses electrons, and one step where a substance is being reduced, which means it is gaining electrons. Okay? So in this particular case, we can write for the oxidation half reaction, the step where oxidation is being spelled out explicitly, the following situation. The carbon here has an oxidation state of -4. It has an oxidation state of +4 on the other side, on the product side. We have done this last time. Do you remember this? Determine the oxidation state, -4 to +4. It loses electrons. It goes from negative to positive. It means it becomes more positive, less negative. It means you lose electrons. This is the definition of being oxidated. Okay? So if you go from -4 to +4, technically that implies that you lose 8 electrons. So we can write that in the following way. Okay? So this is methane, CO2 plus 8 electrons. So I only write here this juncture, what happens to the electrons. You see already, if you look at this equation a little bit more carefully, that in terms of the elements, this is absolutely not balanced. Okay? Because, for instance, I have 4 protons here, or 4 hydrogens here, and I don't have any here, and here's oxygen, nothing here. So this is not a balanced equation at this point. Okay? This is just to show to you that 8 electrons are being generated in this process. In an oxidation half reaction, the electrons appear as products on the product side, on the right-hand side of the equation. Okay? Because they are being generated. The compound is losing them. That means they are a product. In the reduction half reaction, the situation is reversed. Right? Oxygen here receives electrons. Alright? Because it is being reduced. So it actually takes electrons up that come from elsewhere. We know where the elsewhere is. That is the carbon. The carbon delivers it. The oxygen consumes it. So the oxygen is being reduced. It takes those 8 electrons that are being produced by carbon, it eats them up and incorporates them by changing the oxidation state of the oxygen. Okay? We have here 0 on the reactant side, because this is elemental oxygen. On this side, we have -2, because it's bonded to something else in a covalent molecule, and here as well. So -2, -2. There's 2 here. That means -4 in total for this guy. 2 times this one, -2, also -4. Minus 4 plus minus 4 equals minus 8. So a total of minus 8. This is 0. That means that these 8 electrons compensate for the minus 8 that appeared over there. Okay? In the same fashion that these electrons account for the fact that the oxidation state has changed 8 units. From this side on, the oxidation state has also changed 8 units from here to there. So, in other words, these electrons appear either as products or as reactants. In the reduction step, they appear as reactants. In the oxidation step, they appear as products. Okay? So, if you write half reactions, that's exactly what we're going to do. We're going to write the electrons as reactants or products in these half reaction steps. Now, we have to take care of business here, because there's a serious problem going on, like we just indicated. It is not balanced in terms of the elements. It's also not balanced in terms of charges. Minus 8 here, nothing here. This is neutral. So something is wrong, and the same here. This is not balanced by any means. So let's look at another example where we try to balance both half reactions and then try to make sense of this. Okay, so let's look at this example. It's an easier example. It's also an oxidation reaction, oxidation-reduction reaction. This is chlorine gas. It is interacting with iron ions in solution, and it forms Cl- in solution, and the oxidation state of iron ions has changed in the process. Okay, so what we want to do is to split this reaction in an oxidation step and a reduction step, then balance both steps such that the number of electrons that is being produced is the same as the number of electrons that is being consumed. And then we're going to add them up, and we should arrive at a balanced equation overall. Okay? So let's try that. First, we have to find out what is being reduced and what is being oxidized. So let's try to assign the oxidation states of these compounds. This is chlorine gas, elemental. That means 0. That's the oxidation state. This is an ion. That's easy. That's just +2. It's the same as this charge. This one is an ion. Easy. -1. Again, an ion. Same as the charge. +3. We just discriminate the oxidation state versus the charge by reversal of where the sign appears. +3 for the oxidation state. 3+ for the charge. Okay. Second step. Identify what is the reduction step and what is the oxidation step. What is being reduced and what is being oxidized. Okay, so let's look first at the chlorine. Chlorine goes from 0 to -1. That means it gains electrons. Okay, it gains 1 electron per chlorine atom. And the iron ion seems to lose an electron. So that is being oxidized. This is the reduction step. That's the oxidation step. All right, so what I'm going to do now is I'm going to take this reduction step and this oxidation step, and I'm going to balance them relative to one another. So this is how it works. This is the reduction step, okay? Chlorine is going to be reduced to chlorine minus. I recognize very quickly there's 2 chlorines here. That means there's going to be 2 chlorines minuses there as well. All right? So this is now balanced in terms of the elements. But I see very quickly it's not balanced in terms of the charges. So what I'm going to do is I'm going to do that by adding electrons. I see there's 2 minus charge on this side. 2 times 1 minus is 2 minus. That means I have to add 2 electrons on this side as the reactant. Because reduction, half reactions always have electrons at their reactants. There it is. So 2 electrons plus chlorine gas gives me 2 Cl- ions. This is a half reaction that's balanced. Both, oh, bless you. Anyone else? This is the time, it seems. This is balanced both in terms of the elements as well as in terms of the charges. Okay? -2 here, -2 there, 2 chlorines on each side. So this is done. Let's go to the other reaction. The oxidation half reaction. We found that iron, the ion of iron, is being oxidized. Each iron ion loses an electron. Okay, so in this particular form, there's one ion here, one ion there. The number of elements is already balanced in this half step. The charges are not, because this is +2, this is +3. That means I have to add an electron on this side to make this 2+ as well. Okay, so now it's balanced both in terms of the elements as well as the charges, and it's exactly what I expect, because in an oxidation half-reaction step, an electron or multiple electrons should appear as the product. Okay, so that's really good. So both are now balanced in terms of charges and elements, but they're not balanced relative to one another. Okay, because here I see 2, and here only 1. That means the 2 electrons that the chlorine will need is not being delivered by the iron, unless I multiply the whole thing by 2. Okay, so that's exactly what I do. I multiply this reaction by 2 to be able to generate enough electrons that are needed for this reduction step. And now I have the same amount of electrons in the oxidation, and the reduction and the oxidation step, and now I can add them up. So if you want to compare both reactions, you have to make sure they have the same amount of electrons. So let's add them up. These are the 2 half reactions that I found. I see immediately that on this side are 2 electrons that appear as the product, as the reactant. On this side they appear as the product. Just like spectator ions, you can cross them out. If they appear on both sides, cross them out. Okay? And I can add up the rest. So chlorine plus 2 iron, 2 plus, and then 2 chlorine minus plus 2 times iron 3 plus. That is balanced, both in charges as well as in the number of elements. Okay, we can quickly check if that is true. 2 times 2 plus is 4 plus in total. 2 times 3 plus is 6 plus. 2 minus 6 plus is going to be 4 plus. So 4 plus here, 4 plus there. Balanced both in charges as well as in the number of elements. The electrons that I have in my half reaction should cancel out if I add up the equations. Okay? All right, so this is an example of how half reactions can help us understand what happens in a redox reaction, also how to properly balance these equations. This is particularly important if you want to balance redox reactions that happen in solution. Why is that? That is because in solution, oftentimes water molecules and oxygen that is present in the water, or protons present in the water, will partake in the reaction. Okay? As we will see in a few moments, this is going to be essential to balancing redox reactions. And if you do reactions in solution, in aqueous solutions, you have to use the method of half reactions to properly balance these reactions, as we will see in the subsequent slides. Okay, so the message of this slide is the following. Water molecules, H plus or OH minus ions may partake in the redox reaction. So let's look at an example. Here's one. I see here solid copper. It is interacting with nitrate anions in the solution. Okay, so I have a chunk of copper in solution. In the solution there are dissolved ions, nitrates. And the products are copper 2 plus, so now copper is an ion as well. And I have nitrogen monoxide gas. Okay, so I have to balance this, and as you will see, we will need water, H plus, or OH minus, that is part of the solution as well. So in order to balance this reaction, I'm going to do the following step. First, I'm going to write the oxidation and reduction half reactions. Okay, I'm going to determine what is being oxidized and what is being reduced. All right, so the oxidation half reaction, meaning something that loses electrons, I quickly identify that is the copper, because the copper goes from 0 to 2 plus. It's clearly losing electrons. But that must be the oxidation half reaction. The reduction half reaction must be the other guy. this nitrate anion, and on the other end I see nitrogen monoxide. So I'm going to just write it down as follows. Reactant, product on this side. Okay? I'm just going to say this nitrogen here, this nitrogen element is being reduced. And you can verify that for yourself. That indeed, the oxidation state of the nitrogen is changing in this reaction. Now, if you look at this, half reactions, you can clearly see these things are not balanced whatsoever at this stage. So we have to balance each half reaction properly. This guy is going to be particularly interesting, okay? Because there's one nitrogen here, 3 oxygens there, one nitrogen here, and only 1 oxygen here. There's no way, in terms of writing indices or integers in front of these substances, that I can balance it. It's impossible, right? Only way I can balance this is if I take water or H plus into this. And this is exactly what is needed. Okay. So let's try to do that. Let's first start with this oxidation step. Copper is the reactant, copper 2 plus is the product. Clearly not balanced in terms of charges. It is balanced in terms of number of elements. But this is 2 plus, this is 0, so I need 2 electrons there. Right? So 2 electrons need to appear as the product, as they should in an oxidation half reaction. Okay, so now at this particular juncture, I have balanced the oxidation half reaction. Done. Let's go to the reduction half reaction. Let's first look at the oxidation states of these guys, just to kind of like try to understand what is going on. This guy is oxygen bonded to nitrogen. It has an oxidation state of -2. It has 3 of them. 3 times -2 is -6. 1 minus is contributed by the minus charge. That means the other +5 need to be delivered by nitrogen. So +5 is the oxidation state of nitrogen here on the reactant side. On this side, I have only 1 oxygen. It contributes -2. That's the oxidation state. That means that the nitrogen on this side is going to be +2. Clearly, the oxidation state of nitrogen is going to become more negative or less positive. Right? It goes from +5 to +2. It has taken off electrons. Okay. So the problem really arises, I cannot put an integer in front of these substances to balance them out. You can try it for yourself, it never works. We need oxygens coming from elsewhere. I have 3 here, I have only 1 here. Where do they come from? Well, in this point number 2 it says, if you need oxygen, you add H2O. Okay, that means I'm going to add water molecules on this side to make the same amount of oxygen appear on the reactant side as well as on the product side. So I have 1 oxygen here, I need 2 more. That means 2 water molecules. Okay, now the number of elements of nitrogen on each side is the same. The number of elements of oxygen on each side is the same. 3, but I've introduced with the oxygen also 4 hydrogen atoms. Okay? Now, if this reaction takes place in an acidic solution, as is being indicated right here, then you can compensate for these hydrogens on the product side, or whatever side they appear, with adding protons on the other side of the equation. I need 4 protons to balance this out. Can I do that? Yes, you can, because you are in an acidic solution. They are there. Okay? So if you operate under acidic conditions, then you can add protons, either to the reactant side or to the product side. It doesn't matter. In this case, it's going to be the reactant side. So now I have the following. I have 4 protons, 4 hydrogens here, 4 here, 3 oxygens, also 3 there, and 1 nitrogen. So the number of elements is the same on each side. Yes?
Specifically, the reason I'm acidic.
Yes. If it isn't basic, then that is exactly the topic of the lecture after the video. Okay, so we only consider acidic conditions in this particular lecture. Basic conditions, it's a similar trick, slightly different. We use OH minus. Okie dokie. So let's continue with this. We're not done. Okay, number of elements is balanced, number of charges is not. we need to check the number of charges on each side. So let's do that. Here, it says already what I have to add, 3 minus. Why is that? Because on this side, everything is neutral. Okay? Total charge equals 0. On this side, 1 minus sign, 4 plus. That means overall 3 plus. It has to be 0. I have to add 3 electrons to compensate. Can I do that? Yes, you can, because in a reduction half reaction, there should appear electrons on the reactant side. Okay? So this completes now my balancing of the second half reaction. It's quite involved, as you can see. Right? First I balance the oxygens with water molecules, then I balance on the other side the number of hydrogens that I need, that I generated, with protons. And then at the very end, I balance the charges by adding electrons where needed. Okay, so now this step here is balanced both in charges as well as elements. Okay, now let's move on, because this is not balanced yet relative to one another. As you can see, 2 minus here, 3 minus. That's a problem. They have to be the same in order for me to add them up. How do you do that? Well, you have to make them equal. It's only one way to do it. You have to multiply this reaction with something and this reaction with something. The lowest multipliers for that are, in this case, 2 and 3. That means I multiply this thing with 3 and this whole reaction by 2. That's it. Then I generate 6 electrons here and 6 electrons there. That is the same on each side. Right? In the process, of course, I also have to put a 3 here, here, and so forth. So, if you do that, if you write that out, it's going to look as follows. This is the oxidation step. 3 copper 2 plus ions, plus those 6 electrons that I generate. And then for the reduction half reaction that I can add to it, I see on the reactant side those 6 electrons that I will consume. The protons, this was a 4, I multiply by 2, so it becomes 8. And then this is the 2 that I multiply this nitrate with, so 2 nitrogen monoxides, and 4 water molecules. Okay? You can add these things up, and what you find is the following. 8 protons and so forth, and you see that on each side appear 6 electrons. They can be crossed out at this point. So they can be left out, and what you're left with is these compounds generating these compounds. That is the final step in my balancing of the redox reaction here. I want to make sure that I did this correctly. Okay, so I'm going to count the number of elements on each side, and also check the charges. Let's do that. Don't worry, it's the same reaction. We try to write this down. Here it is, the same. I'm just going to count the elements. Let's start with copper. 3 copper here, 3 copper there. Check. 8 protons here, or 8 hydrogens. Also 8 hydrogens right there. I have 2 nitrogens right here, 2 nitrogens right there. And then the number of oxygens. 6 from here. And then 2 from here, plus 4. That's a total of 6. Okay, so I find indeed that all the elements are balanced in this reaction. As they should. Okay, let's see. Oh, that's too quick. Let's also check if we have the charges balanced. Okay, so here I have 3 times 2, that is 6 plus. 6 plus, 8 plus, 2 minus, that means also 6 plus on the reactant side. So on both sides, I have a total charge of 6 plus. So in terms of the charges and the elements, this reaction is finally balanced. So you have all these little checks you can perform to find out if you're on the right track. Okay, well, this is the round and ball, so let's do another one here to see if you get it. Same conditions. Acidic conditions, that means I can use water and protons for balancing half reactions. In this particular case, I have iron ions, 2 plus again. They're being converted into iron 3 plus ions. And I have on the reactant side ions here called permanganate ions. Okay, MnO4 minus. And then on the other side, I have manganese 2 plus. Okay, Okay, so I'm going to proceed in exactly the same fashion, taking the same amount of steps as before. I want to start with writing down the half reactions. This is one half reaction I recognize. This is permanganate ions, okay? And on the other side, the manganese ions. I recognize that this manganese element is changing its oxidation state. Okay? If you look at this, this is going to be oxidation state 2 minus, 4 of them. That means, and this minus sign, that means this must be 7 plus, this is 2 plus. So it goes from 7 plus to 2 plus. It gains electrons. It gains electrons. I can already say it gains 5 electrons in the process. Okay? So this, if it gains electrons, must be the reduction step. This is the reduction step in the redox reaction. The other guy then must be the oxidizing step. Oh, there we go. Good. I was right. You see here, iron is going to be converted from 2 plus to 3 plus. It becomes more positive. Oxidation state becomes higher. It means that you're losing electrons. Okay, that means you're being oxidized. So this is the oxidation step in the redox reaction. 2 plus to plus 3. Okay, so what I have to do next is to balance both of these reactions independently and then relative to one another. This one is going to be easy, I can tell you that, because there's no oxygens or hydrogens appearing in this reaction. Only charges have to be balanced. This guy may be a little finicky. Oxygens here, nothing there. So I'm going to need the waters to balance this one out. Okay, so let's do that. Let's start with this guy, the reduction half reaction. Okay, so I see here in terms of the manganese elements, the same amount on each side. So that's good. The oxygens is a problem. I have 4 oxygen atoms right here, nothing there. So I have to add 4 water molecules. These 4 will give me 4 oxygen atoms that I need to balance out the oxygen inside. However, in doing so, what I also introduced is 4 times 2, it's 8 hydrogen atoms that are not present on this side. So I have to add those in terms of H plus. Okay, so let's do that. I add 8 H plus ions, 8 protons to, in this case, the reactant side. Okay, very good. In terms of the elements, I am balanced at this point. Okay, hydrogen, oxygen, and manganese are all balanced. What is not balanced is the charge. Let's count, for instance. This is 8 plus, that is 1 minus, that combines for a total of 7 plus. Okay? On this side, I only see a 2 plus, and that's 0. So that means 7 plus, 2 plus, they're not matched in terms of charges. This one is less positive than this one here. I need to bring this down by adding electrons on this side. Okay? So if I add 5 electrons, 7 minus 5 equals 2. Then I'm balanced in terms of the charges as well. And that is exactly what I need. Okay? Because in the reduction half reaction, electrons should appear as the reagent. Now another double check I can apply is I saw already that the oxidation state of manganese is changing by a total of 5. That is exactly the 5 electrons. Okay? That is being consumed by the manganese atom to change its oxidation state. Okay? Since there is an integer, the integer here is 1 in front of the manganese, I need only 1 times a portion of 5 to change the oxidation state. If there will be a 2 here, it will be 10. Okay? So this is another double check you can apply. You can just really decipher this entire equation using all those checks. Okay, let's look at this guy here, the oxidation half reaction. A lot simpler. No oxygens or hydrogens needed. Just balancing the charges. So already 1 element here, 1 atom here, 1 atom there. That's taken care of. 2 plus, 3 plus. I only need to add 1 electron, in this case, on the product side. Okay, there it is. If I add this electron, both sides are going to be 2 plus. Okay, both half reactions are balanced with respect to themselves, but not with respect to the other guy. That means what I have to do is I have to find multipliers to make sure that the number of electrons being generated in the oxidation step are the same amount as the electrons needed in the reduction step. Well, I see that this is only 1, this is 5, so that's not so hard. I just have to multiply this equation by 5. Right? If I do that, I generate 5 electrons. Those are the 5 electrons that I need to get the 5 electrons into the reduction step. Okay, so then, at this juncture, I want to add them up. So there we go. I have already added them up for you. I add up the oxidation and reduction reagents. And then on the other side, I'm going to add the oxidation and reduction products. And you see, indeed, 5 electrons here, 5 electrons there. They can be crossed out. Okay? And what I'm left with is this here and that here. So the very last step I'd like to take is to check if I did everything correctly. That means that the number of elements have to be balanced on each side, and the charges have to be balanced as well. So let's do that. It takes 30 seconds. There we go. On the reactant side, I see 5 irons, 1 manganese, 4 oxygens, and 8 hydrogens. And on this side, 5 irons, I see 1 manganese, 4 times 1 is 4 oxygens, and 4 times 2, 8 hydrogens. So this is the same on each side. Elements are balanced. Okay? That's what I just said. Here, charges. Let's check that too. On the reactant side, what do I have? I have 5 times 2 here for the iron. For the manganese, I have -1, this whole thing, permanganate ion. And then I have 8 times +1 here for the hydrogens, for the protons. If I add all these up, I have 17. Okay? 10 minus 1 plus 8 equals 17. So the total charge is 17. It's a very odd number. It doesn't matter if it's odd. Okay? As long as it is the same as the other side, I'm fine. Let's check the charges on the other end. I have 5 times 3, then I have 2 plus, and then 0 for this. So this is 15 plus 2, 17. Hallelujah, I am ready. This balances beautifully. So balancing these equations seems a little laborious, but the steps are very straightforward. Okay? If you apply them just strictly as we did right here, you can't go wrong. Can't go wrong. Any questions, folks? Does it make sense? Very good then. See you on Wednesday.